All right.
You want to wait a few more minutes?
Yeah, and let's say hi to everyone and welcome. Thanks for coming along. If it would be great if you could all turn on cameras, because for a moment we could say hello, and then we'll begin once everyone has joined in. Hi all. Oh, good. People are still gathering, so there's still a moment. It's really nice to see everybody, despite the fact that we're all very distant. But happily, here in the building of the NBRI, I'm sitting one floor up. Tanya is one floor down, as are Duigu and Bo Yuan and Zijian, who are sitting in the lab, and others who are all online. And I see that we have people from all over the world, indeed. So let's begin. Very warm welcome to everyone to today's lecture. Our speaker this afternoon, at least it's afternoon here in Israel, our speaker this afternoon is Tanya Bloch. Tanya has a bachelor's degree and a master's degree from the Technion in civil engineering, master's with a specialization in construction management. And she's now coming to the end of her PhD work. We hope that she will submit her thesis by the end of the month. And her topic, as you can see, is an evaluation of computational approaches for semantic enrichment of BIM models. This is a topic that's already at the forefront of building information modeling research these days internationally, because it's a growing idea and technology that has the potential not only to work well for code checking or design review, but in general for solving interoperability problems, which despite 25 years of IFC and building smart, problems that still dog the industry and keep us back from advancing. So Tanya, I'm going to stop there and welcome you and welcome everyone else and ask you to take the floor.
Right. Well, good afternoon, everybody. Thank you for the introduction. So I'm Tanya. I'm going to talk to you about my research, evaluation of computational approaches for semantic enrichment of BIM models. Let me just, yeah. Okay, so I will begin with a short background on semantic enrichment and automated code checking and the connection between the two, which should also explain the motivation for this research. We'll present the research hypotheses, research goals and methodology, and then the accomplished work, which was divided into two phases, clustering and validation, and then some results, conclusions, and suggestions for future research. So semantic enrichment of BIM models is a relatively new field of research. It is defined as a process where domain expert knowledge is used to infer the semantics of a given model, and then that inferred information can be added to the model and we get a new and improved and enriched model. Another way of looking at it is by saying that we want to identify all the implicit information in a model and represent it explicitly. So in general, we know that BIM models are sources of very rich information about the building elements, their geometry, their properties, and their relationships. And all this information is stored in a computer readable format, which should also make this information reusable. So we should be able to export information from the authoring tool and use it for many different applications, such as for automated code checking. And this is exactly why the industry foundation schema was created. The industry foundation classes schema was created to enable us to make this exchange. And this is today the common way of sharing information in the industry. On top of that, we have the model view definitions, which are subsets of the overall broad IFC schema that are designed to fit a specific use, a specific workflow. But the problem is that even if the information is not explicitly represented in the model, then it can't be exported to IFC or to any other format for that matter. And so this information becomes information that we cannot reuse. And there's actually quite a lot of implicit information in any BIM model. And here's an example. So this is a floor plan of a building. This is taken from a model of a building here in Tel Aviv. And well, we can quite easily see and understand that this is a residential building, that there are 6 apartments on this floor, that there is a single security room that serves this floor instead of by the way, the common way for new construction in Israel, which is a shelter in every apartment. But this information actually is not necessarily represented in my model. So if I create the space elements or not, this will look exactly the same to us. I don't have to create the spatial elements or the zones that define a single apartment, and still we understand that this is one apartment and this is another, and this is a public space, and so on. So we understand beyond what is represented in our model. And if we look at this in the context of code checking, when we do it manually, we know and understand the requirements of the codes. We also understand both the implicit and explicit information of what is represented in the design in front of us, and we have the full picture, we have the complete information, and we can make a decision. But the computer can't do that, not yet anyway. So if the information is implicitly represented, then it's simply missing. It's a missing piece of the puzzle. And it's not the only one, because in many cases, even if we do explicitly represent information in the authoring tool, the representation may not match the requirements of the receiving platform. And so in terms of the receiving platform, this is yet again another missing piece of the puzzle. And here's an example of that. So if I want to model the foundations for this building, I can either place a footing element in my model, but I can also just model a simple slab, define that it's made out of concrete, and put all the reinforcements in all the right places. And it will look exactly the same to us. And we will all understand that this is the foundation. But if my receiving platform, let's say a structural analysis platform, is expecting an IFC footing in the input IFC file, then I'm going to have a problem. So there is missing information and there is misrepresented information, and still we do have today functional commercial applications for automated code checking. One of the most known and advanced and used is the Solibri model checker. Solibri is a rule-based application. It contains sets of rules that are based on the requirements of the International Building Code, and it receives an IFC file as input. Then the user can select which of the rule sets he wants to apply to his model, and he gets this very visual, graphical report of all the rejects that were found. Here is an example of what Solibri can do. So this is part of the accessibility rule set check. One of the requirements from the code is for a certain size of a circular space to be available inside an accessible background. And so what we can see here, those are the results of the checking. So we can see the green is the available space, the red is what is required by the code, and obviously there's a problem here and we need to go back to the model and make changes. So this seems to be working perfectly, but if we take a closer look at what happens when the user is trying to initiate such a check, the first thing the user gets is this to-do list, like you see right here. So this contains all kinds of tasks. You see space usage classification and many different parameters that the user is expected to fill in before the checking can begin. This is basically Solibri asking the user to fill in the missing pieces of the puzzle, to supplement all the information that is required so the rules can be executed. And if we take a closer look at the space usage classification task, first of all, it makes sense. I can't check for the requirements of an accessible bathroom if I don't know which space in my model is the accessible bathroom. But in this case, the spaces were actually created and named and tagged in the authoring tool. The name column that you see right here, this comes from the input IFC file. But Solibri does not recognize non-accessible. It only knows what accessible toilet is. So the user is asked to do this kind of mapping between the way that information is represented in the authoring tool to the way that Solibri is expecting it to execute the checking. And if you think of a large building with lots of spaces like this one, then this actually becomes quite a lot of work. And also taking you back to the situation I just showed you with the accessible bathroom, if I now need to go back to my model and make changes, that means I need to export a new IFC file, which means I need to go through this entire process all over again. So this is actually true not only for Solibri, it's true for all the existing rule-based applications for automated code checking. And just in general, if we look at the process for automated code checking, it will usually contain 4 stages. So we have interpretation of rules, then we have the pre-processing of the BIM models, and then rule execution and reports. So interpretation of rules, this means that we need to translate hundreds of written documents into something that is readable to a computer. And this is a field of research on its own, and it's outside the scope of this work. The second stage, pre-processing of BIM models, this is actually exactly filling in the missing pieces of the puzzle, supplementing all the required information so the checking can begin. And this is, as I showed you, done manually today, and it contains a lot of work. And so this is the point where we think that semantic enrichment can really benefit this entire process, because it offers a way to automate the stage. And by automating the stage, we may be able to get a higher degree of automation in the entire process of automated code checking, maybe even for a wider range of information. And so this is exactly the first hypothesis of my research, that is that semantic enrichment can solve the challenges in preparation of input information from BIM models in a form sufficiently precise to enable automatic code checking for a wider range of information. To try and prove this hypothesis, I focused on a task that would be relevant for many code requirements, and that is the classification of functional spaces in a building. More specifically, I focused on trying to classify room types in a residential apartment. But this is not the first classification task that was solved by semantic enrichment. I am referring to the Seabridge project, where a model of a bridge was obtained from a concrete bridge, was obtained from point-cloud data. So the model did not contain any semantics at all. All it contained was geometry, and well, a beam didn't know it was a beam, and a column didn't know it was a column. And one of the tasks was to try and classify all those instances. So to do this, this was done by compilation of rule sets, but based on logical statements. So one of the rule sets was based on the geometric features of every element that we expect to find in the model of a concrete bridge. And the second rule set was based on the relationships between those elements. So for example, we know that a deck slab will always be above the columns. Those two sets of rules were implemented in an engine called CBIM, which is a rule-based engine for semantic enrichment. And the result of this was correct classification of all the elements in the model of the bridge. So naturally, I tried to do exactly the same thing with the room types, except for spaces, there are very few geometric features that can really distinguish between the different functional spaces, because a space is basically a box. So the spaces vary in size, they vary in the number of faces they're defined by, and those spaces can be either physical elements, such as walls, or they can be virtual boundary lines, But almost every rule that you compile based on those features will not lead to predefined fixed outcomes. For example, I can't say that if the size of a room is 12 square meters, then it is a bedroom. That will not always be true. And when it comes to the relationships between the spaces, then it's the same thing here as well, because turns out there's quite a lot of variety in the layout of a standard Israeli apartment. And my ground truth in this case was 32 models of apartments that I received from the industry, so that was quite representative. And here again, most of the relationships that we identified did not lead to predefined fixed outcomes. We ended up compiling 14 rules, so also based on the geometric features as well as the relationship features. And those rules were represented as matrices, just like it was suggested and implemented in the Seabridge project. So here is an example of such a rule. This is room 1 always larger than room 2? And the values that you see here, the Y, that's a yes, the N is a no, the X is a maybe, that is a sometimes yes, sometimes no. This is exactly the type of values that will not lead me to fixed outcomes, and you can see that the matrix is quite full of them. Now, when you look at a single cell and you string together the values of that cell across all the 14 matrices, if you are able to identify a unique string, that would mean that you are actually able to identify, classify the elements that this cell represents. And as I said before, the X is sometimes a yes, sometimes a no. So this is not a unique value. So in the end of this process, we were able to only identify 5 such unique strings, which means we could only classify 5 functional spaces instead of out of the possible 15 that we had represented in our apartments. So I was looking for an algorithm that will allow me to represent all those maybes, all those X's, and still be able to classify all the 15 possible functional spaces. So I tried to solve the same problem with using a machine learning algorithm, a supervised machine learning algorithm. In this case, an artificial neural network was used. So the idea now is that I don't need to compile rigid rules. All I need to do is to provide examples, and I had my 32 models to compile a training set of examples based on them. So now, once this algorithm is trained on my data set, it should be able to generalize from the data set and to make predictions on new instances that we present. This procedure was implemented in a platform called Microsoft Azure Machine Learning Studio, which is a platform that allows you to apply many different machine learning algorithms on a data set that you compile. So to compile the data set, as I said, I used the models of apartments that I received from the industry. I created the space elements, I labeled them, and then each instance, each space was assigned with a vector of features. So here again, I used both the geometric features as well as the connection, the relationship features. More specifically, the ability to directly access one room from another was used as a relationship features and added to the process each time that the space was labeled. This iterative process was then applied to make predictions on 3 test cases, 3 apartments. And as you can see, the result of that was correct classification of all the spaces in all 3 apartments. I did also try to solve the same problem by graph representation. So since we understand the relationships between functional spaces will ultimately define the whole layout of an apartment, I represented each apartment as 2 graphs. So I had an adjacency graph and an access graph, and then the features could be extracted from those graphs, which means that eventually in my data set, every instance becomes a pair of spaces instead of a single space, which carried quite a lot of problems with it. And you can also see that I could not get as good results as I did with the previous algorithm. So only 70% of spaces on a test case were classified correctly. But this experiment led me to the conclusion and to the second hypothesis of my research, and that is that there are actually several types of information that we must supplement to enable automated code checking, and that each such type may require a different approach for inferencing. So based on this, two research goals were set. One was to identify the classification, the different classes of semantic enrichment tasks that are defined by information that is needed to be supplemented to enable an automated checking, and then to match each such class with the most appropriate computational approach for solution.
We will shortly be arriving.
Enrichment. I'm going to mute all of you. I'm sorry. Okay. All right. So to achieve those goals, the work plan, the entire research was divided into two phases. So I had the clustering phase and the validation phase. In the first phase, in the clustering phase, I analyzed codes that serve as test cases to identify all the concepts and all the properties that will be candidates for semantic enrichment. Then a cluster analysis technique was applied to this entire list, and we formed, by this clustering technique, we formed an initial data structure. Then to validate this data structure, we defined representative experiments from every identified class, and the results of those experiments led us to update the data structure and to match each identified class of semantic enrichment tasks with the most appropriate recommended method for enrichment. Methodology. So since I am dealing with describing an existing problem through data collection, then we can say that this is a descriptive research. But also the second phase of this research, I drew conclusions from single experiments that I assume are applicable to the entire group that every experiment belongs to. So the second phase of this research has an inductive nature to it as well. These are the test cases. So these are the codes that were chosen to be analyzed, and you can see that there are 5 chapters from 5 different codes here. We did limit the scope of this research to dealing only with geometric requirements, but we also tried to select the codes to have a variety of both general concepts, general building concepts, as well as very domain-specific concepts. And also you can see here that one of the codes is a local code of the Israeli Code for Security Links. Here is the general outline of phase 1. So we began by analyzing the chosen codes to identify all the concepts and all the properties that are represented in those codes. Now we excluded from this list all concepts and properties that we expect to be represented in the coordination view, model view definition, because those will not require us supplementing them. We assume they will be present in the IFC file. We are then left with a list of concepts and properties that are candidates for semantic enrichment, and those are defined as enrichment tasks based on the context of the code requirement they came from. Then they are characterized, assigned with feature vectors, and a cluster analysis technique is applied to identify the different classes of semantic enrichment tasks. So how did we analyze the codes? The codes were analyzed manually, first of all, and here are 2 examples. So the first one is from the International Building Code. The means of egress shall have a ceiling height of not less than 7 feet and 6 inches. The means of egress in this case is a concept. It is a domain-specific concept that you are not going to find in IFC. And the ceiling height is, of course, a property of that concept. And here's a little more complex example, and I am going to talk about this specific code requirement a lot more in a few slides. So this is from the Israeli Code for Security Rooms. So at least 70% of the cumulative length of the walls of a security room must be directly supported continuously through to the foundations. So walls of a security room, that is actually a concept. Those are the specific walls that bound a security room. Directly supported continuously, and the cumulative length of the walls, those are, of course, properties. So the cumulative length is a property of every security room. And this is, of course, a value that you're not going to find in the IFC, but it's also not a value that is, it doesn't make sense to ask a user to manually supplement this value because then there will be no point to automating checking of this requirement at all. Most of this work is in calculating this value. So now, after the concepts and properties were identified, we defined specific enrichment tasks based on the context of the code requirements that they came from. And here are some examples of that. So we have create the geometry of the means of egress, classify spaces to identify security rooms, associate walls to security rooms, and finally, calculate the supported length for every wall of the security room. The phrases that you see in red actually repeated for all the semantic enrichment tasks that were defined. And even more than that, we could see that all the concepts were defined as creation tasks and association tasks, and all the properties as classification and calculation tasks. So just by doing this, just by analyzing the codes and just by identifying the need for enrichment and defining the enrichment tasks, we could already see the initial data structure beginning to form. Now, to create one more level to this and to identify the subtypes of each such group, we applied cluster analysis. So every semantic enrichment task was analyzed and assigned with a vector of features. And you can see the list of features that I've used for concepts up here, and the list of features I've used for properties here. And you can also see that those are not identical, which also shows that concepts and properties should really be two distinct, separated groups. Once we've done that, we've applied K-means algorithm as the cluster analysis algorithm, and this was also implemented in the Azure Machine Learning Studio. Here are the initial results. Those are actually the results of phase 1. So we can see that for creation tasks and association tasks, 2 subtypes of semantic enrichment tasks were identified. And for the classification and calculation tasks, we identified 3 subtypes for each. And now the idea is to validate this initial data structure with respect to the most appropriate method for solution of each identified class of tasks. So we defined experiments, representative experiments that were based on requirements from the codes that were analyzed. And actually, well, except for the room type classification experiment, the others, each requirement actually translates to several semantic enrichment tasks. And those tasks are spread between the different classes of enrichment types that were identified in the first phase. The results of those experiments and the conclusions that we could draw from those results led to an updated data structure and to matching a most recommended approach or method for solution for each type of pass, which ultimately led to creation of this kind of roadmap for semantic enrichment to support automated code checking. So here is an example of an experiment, and this is a code requirement that I already showed you. So just to understand what this means. Again, at least 70% of the cumulative length of the walls of security rooms must be directly supported continuously through to the foundations. So first of all, security rooms must be stacked one on top of each other to make a security room shaft. And now you can see an example of such a shaft here. So on the first floor, you see that the east wall from this room is missing, but still we are left with more than 70% of walls that are supported by the foundation. And so this room will pass. It's compliant to the code, it's fine. On the second floor, the wall is here, but it's not continuously supported because it is missing on the first floor. It will pass still because there are still more than 70% of the walls that are continuously supported. And on the third floor, you can see that this wall is missing as well. So this is missing, this is not continuously supported. We are left with less than 70% of the walls that are supported continuously through to the foundation. And so this security room is not compliant to the code, it will fail. And so will all the security rooms above it. This single requirement from the code actually translates to 6 semantic enrichment tasks. So most of them are association and calculation tasks, but we also have the classification of room types to identify the security room. Then we have the associate walls that belong to security room to the security room, identify any walls or foundations that support each wall and associate them with it. So I would associate the foundation wall to this wall and this wall to this wall and so on. Then for walls supported by foundations, calculate the portion of their cross-section that is supported and store the value. For walls supported by walls below them, calculate the portion of their cross-section area that is supported by the lower walls supported area and store the value. So every time I go up, I actually store the values. I carry with me information about the supported cross-section from the wall below. And finally, calculate the total value of the supported walls for each security room. So this is actually the final test value. Based on this, I will be able to check my model for compliance. So to represent this final test value, we compiled a set of rules and implemented those rules in the BIM engine on a model that we obtained from the industry. So this is a residential building with 8 floors and 3 underground parking floors, and it contained a single security room shaft. On the top of the slide, you can see an example of an individual rule out of the rule set that we compiled. This is specifically to deal with the association task of associating all walls that belong to a security room with it. Basically, in all of the rules, we apply different operators on every pair of objects in our model, and then we store different values as attributes of the elements based on what is defined in the rule. And those values can be either numeric numbers, they can be results of some calculations, or they can be simple tags or texts. What you see on the bottom of the slide is actually the final checking algorithm. So because we extensively enrich the model to contain the specific final post-test value, the checking of the model actually becomes quite simple. It comes down to a single if statement. So we added one more rule to our rule set, and we were actually able to check the model as well as enriching them. And so the final result of this would be pass or fail for every security room in this model. You can see the entire process in this short video. So this begins with the input IFC file, just shown in a simple viewer. The spaces were actually created and classified before this experiment because this was not the focus of this experiment. Here are the walls of the security rooms. Now notice that, for example, the description field here is empty. and it's going to be filled with values. This as well is going to be filled with values after the model is enriched. So this is imported to the CBIM engine, and here is the rule set that we compiled. And again, I remind you, the rule set contains all the rules for enriching the model, as well as the rules for checking the model. So the end result here will be pass or fail for every security room in the model. Here's an example of an individual rule out of the entire rule set. And now, once the CBIM is, once this is done, CBIM actually creates a new IFC file, an enriched model, an enriched IFC file that contains all the information. And this is, you can see it right here. So now when you take a look at a security room, you can see that it's tagged as pass. So this specific security room is compliant to the requirement that we are dealing with. For the walls, notice that now the description field is no longer empty. It contains the tag that connects the wall to the specific security room. And also the values that you just saw, and here you can see them again. Those are actually the endpoints of the supported cross-section from the wall below. So to sum this up, all the clusters that we've identified in the first phase were explored through experiments, either experiments that we defined in this work or experiments that were conducted in the secret project. And although we focused on single experiments, single tasks from every identified class, we also looked at the clusters as a whole to try and identify tasks that did not belong in the context of the expected method for solution. And finally, the rule-based approach was a default approach for us, so it was explored in all the cases. This is the final results. So this is the roadmap for semantic enrichment, and you can see that the data structure was updated, and a recommended approach for solution was assigned to every identified class of enrichment tasks here. So for example, creation tasks in the first phase only contained 2 subtypes, but now one of them was split into 2 because it requires a slightly more complex method for solution. So you can see one of the classes is abstract aggregations, such as, for example, an apartment or the means of egress, which are aggregations of spaces. And this is assigned with the rule-based approach with a prior graph analysis. Then we have the abstract concepts that are dependent on other model elements. This group actually contains tasks of creating elements with an unknown size and local placement because they depend on all the other elements in the model. And so this will require an iterative algorithm for solution. And then we have the abstract, simple abstract 2D or 3D elements that are assigned with a rule-based approach. The association tasks actually contained 2 subtypes in the initial clustering phase, but now they were merged into a single group because we could not find any difference in associating between physical elements and associating between abstract elements, which was the distinction in the first phase. So now we have a single group for that. For the classification tasks, we have the general classifications that are assigned with the rule-based approach and the classification of functional spaces that are assigned with a machine learning approach, assuming, of course, there's an appropriate data set for this. And finally, the calculation tasks. So we have the calculations that are based on topologically complex relationships, just like the requirement that I just showed you. And this is assigned with the rule-based approach, but it will also require storing of many intermediate values as attributes of the different elements, which could be significant when trying to solve more than one task at a time, more than one requirement simultaneously. And finally, we have the independent calculations or the more simple calculations assigned with a rule-based approach. So as you can see, most of the classes that we have identified were assigned with different rule-based computational methods. And I also said that the rule-based approach in general was our go-to approach, was our default approach when dealing with experiments. And I also think it should be the default approach when dealing with semantic enrichment as a whole. And there are a few reasons for that. So first of all, some of the identified semantic enrichment tasks can be solved by a small set of easily defined logical statements. And there is really no justification in trying to solve a very simple problem with a very complex solution. Another reason is the issue of data availability. So while rules require us to be engineers, you know what we know, and define what we know as a set of rules when it is possible, of course, machine learning requires data, lots of data. And this data is not always easy to obtain and to maintain. And also, it's not so easy to extract from the building models. And we should also remember that we can't just collect models, all the models that we can get our hands on, because the data set needs to fit the problem that you want to solve. And finally, liability. So this is focused on automated code checking. And so we should remember and keep in mind that machine learning algorithms are probabilistic. So while we are guaranteed to get a solution, nobody guarantees that the solution is correct. While with rules, if the rules are compiled correctly and the information is correctly represented, then you have a very high assurance that the solution you get is correct. So you can say in this case that rule-based approach is less risky than a machine learning approach. But we also saw, on the other hand, cases where rule-based approach simply does not provide a solution, and those cases will of course benefit from a machine learning approach. Limitations. So as I said before, this is a descriptive research that focused on analyzing past cases, and so we cannot guarantee that all possible classes of semantic enrichment were identified in this research. Also, in the second phase, we drew conclusions from single experiments, and we assumed those conclusions are applicable to the entire group that each experiment belongs to, and this is something that we, of course, cannot prove as well. And finally, additional approaches that for semantic enrichment that we may have not recognized yet could exist, and they were not analyzed in this case. Contributions. So up until today, you could really randomly choose to, for example, apply a very complex algorithm to solve a very simple problem, because there were no guidelines. There were no guidelines as to how to identify the need for enrichment, how to define an enrichment task, how to characterize it, and how to select the most appropriate or the most recommended method for solution. So you could do whatever you want. So this research contributes to the foundation of the knowledge in that field in general, and semantic enrichment in general, but also in the context of automated code checking. We can now see that semantic enrichment and automated code checking are two complementary processes, and that one sets the requirements for the other. And we could also see that we are able, by semantic enrichment, to automatically represent a very wide range of information. And so progress with semantic enrichment could very well lead to widening the scope of requirements that we can check automatically. In the minutes I have left, I'm going to talk about the view to the future of automated code checking as we see it. So what we would really want to do is to be able to check the model without the need to pre-process the model and without the need to represent code requirements as rules. And this might be possible by applying a deep learning technique as the checking regime. But we are not able to do that yet. All of the existing applications for automated code checking today are rule-based. So we did explore the idea of applying machine learning as the checking routine, not deep learning, just supervised machine learning. And we did this by trying to check models of security rooms for compliance to 16 conditions from the Israeli code for security rooms, all simultaneously. And so to do this, we had to train a machine learning algorithm. And we did this by creating an artificial data set of models of security rooms. And this set, those models were actually extensively enriched, but they did not contain the final code plus test values for each of the 16 conditions that we wanted to check. Now, once the algorithm was trained, it was applied to additional 20 test cases to make predictions. And the result of that was that we got correct classification of 18 cases out of the 20, only 2 false positives. So first of all, we can see that machine learning is indeed applicable as a checking regime for automated code checking. But we can also see that there's kind of a trade-off between semantic enrichment and automated code checking. So the more effort you put to semantic enrichment up until the point that you actually represent the final test values, then the checking becomes very simple. It comes down to a single if statement. But the less effort you put into semantic enrichment, the more complex your checking algorithm becomes, up until the point that if you do not enrich the models at all, then you might be able to check them by applying deep machine learning techniques. And this trade-off you can see on kind of a spectrum of semantic enrichment versus automated code checking. Now, the right side of the spectrum was not explored yet at all. The research that I presented just now was focused on the left side when specific test values were explicitly represented. And we took one more step to the right, but with, I really think that this research also identified classes of enrichment tasks that will require very complex computational methods for solution. And so I think that future research should focus on trying to eliminate the need to engage in those specific complex enrichment tasks while still be able to check the models automatically by applying machine learning. And this is all I have to say, so thank you for listening.
Oh, okay. Thank you very much, Tanya. Let's all just begin by, I see many of you have already reacted by showing hands, and so I encourage you to do that, even though muted. And let's roll on straight to the questions. Tanya, we have questions from people in the chat. Since we're 24, 26 people, I think we're not too many. There's a great question from Jimmy at TUM. Jimmy, perhaps you'd like to turn on the camera and unmute yourself and ask the question yourself directly.
Of course. Sorry, I was speaking on mute.
Yeah, no problem.
So yeah, thank you for the presentation. Really very interesting work. Yeah, so my first question was about the rules. So I like how you formulated the rules. And so we have a lot of different projects in assisting the design process using building codes or regulations and rules. And I was just thinking, for example, if we have a building and now you're trying to make the interior layout, maybe using this kind of rules, if we don't check for a specific space name, maybe we can, using those rules, find out where is the best location for a security room, or how we can design the floor. So I was just thinking if this kind of rules can be helpful for supporting the design process.
Yeah, I agree, and I think I saw some research projects that are beginning to do this. It's kind of an automated design I'm not sure the interior design, but something like that is beginning.
Because there is they call it prescriptive design. Yeah. And it's like you try to design according to regulations and to building codes.
Yeah.
Yeah. So you think this kind of rules maybe can, I mean, it can handle different kind of complexities to encode some regulations inside them.
I think so, yeah. And the regulation that I just showed you, the security room, that is actually quite complex. I mean, I only had 45 minutes, so I couldn't show all the complexities, but yes, those are very complex relationships that were analyzed and compiled into rule sets. So yes, I do think that rules can handle very complex situations.
Mm-hmm. Okay, thank you. Okay, one last question. So currently you are also working a lot with the building codes, and we see a lot of vague or really sometimes even funnily described rules that you can't figure out the exact meaning behind them. So I mean, sometimes we think, so how can we represent this in a computer readable way? And we always think maybe they kept it vague because I mean, Word is not white and black, and they like to keep something gray in between. So I was just wondering if you encountered similar cases in those chapters you looked into, specifically for this kind of security room situation.
Well, we dealt with single chapters from the codes, so I didn't encounter anything funny like that, but I know it exists. I mean, taking, for example, the security room code, it actually had, I don't know how many appendixes. So just making sense of everything together, that is a challenge by itself.
Yes. Yeah. Yeah. As you said, there's a huge field behind this.
Yes.
Okay. Thank you. Thanks also, Professor Sachs.
Sure. Anyone else, perhaps? Feel free to raise a hand, unmute, raise a question. While anybody is getting ready, Tanya, I will just add that much more recently now, we have looked in Itai's work at this possibility of using optimization with genetic algorithms for semantic enrichment to go from architectural to structural models. And well, I mean, Itai presented that something like a month ago, but it adds one more tool to the palette of different tools for semantic enrichment. A fairly unexpected one.
Yes. Okay.
Hi, Tanya, I have a question. This is Jen. And in your previous slides, a review to the future, you mentioned that in the future, we may use some machine learning ways to achieve automatic code compliance checking. Like that, you think right now we can't do this task, is that right?
Not with deep learning, not yet, because we don't know yet how to represent a whole building model without enriching it and without specifying specific test values as inputs to the machine learning algorithm.
Okay, so you think maybe this is the data problem, is that right? We don't know how to construct the data, but we believe the algorithm maybe could achieve this task in
I think so. I think so.
Yeah, I have. Sorry.
Go on, again.
Yeah, I have another question. You mentioned in your previous work about graph presentation. To my understanding, you use two graphs, but both of the two graphs can only present the relationships of rooms. Is that right?
Yes, that is correct. But the data set actually contained both the features that were extracted from these graphs as well as the geometric features of the space.
So you try to use the relationship of rooms between rooms to classify the type of room, but yes, the accuracy is not really good.
No. Yes, yeah, you're correct.
Yes, but in your previous work, you try to use some geometric data, but the geometric data to class the room type will achieve a better good result.
It turns out it does. Yes.
So this is my question.
It also depends on the data set. You need to understand that with the graph representation, each instance in my data set became a pair of spaces.
Yes.
And so the feature vector grew, and the instances also grew, and the relationships between them didn't really are not compliant. So I don't know. I think this is something you should still try and explore, because I'm not sure that the data that I had available for this was enough. And so, yes, I think it should be explored more.
Yes, this is my question, because you use geometric data to achieve really good results, and you also try to use the relationship, but the results is not really good. I just wondering, can we just combine all the data, including geometric and relationship? Could we achieve better results like that?
It will probably do so, but you need a much larger data set to do that.
Yes, exactly. It seems that in our field, the algorithms are existing right now, but how to construct the data set, how to construct our field data set is a really big problem. This problem maybe is bigger than choose which algorithm in machine learning field.
Well, I think it's true for every problem you try to solve with machine learning. The biggest thing is the feature engineering. So yes,
yes, exactly.
Great. Alon has a question, and Karim has a question, and he wrote that he's on the train, so he's going to write the questions written up on the chat. So let's just go for Alon, who asked first, and then we'll move to Karim, and we'll wrap up. Alon.
Okay, thank you. First of all, Tanya, thank you very much for your great presentation. I have just a little question about, can you show some statistical results, like precision and recall in the labeling of the new instances?
For which algorithm? For the machine learning algorithm, yes. Not right now, but yes.
Okay, do you remember any results or something?
Wow, this is a tricky question. No, I don't. I'm sorry.
Okay.
But you can provide the papers where it's.
But yes, it is provided in the papers.
Okay, great. Thank you.
So Tanya, if you could send those to Alon afterwards, that would be helpful.
Sure.
Karim says.
I will read it. Thanks.
Karim asks, very interesting and thanks for sharing with us. My question is from the clauses you analyzed from the 5 different codes. Can you please give a % of them that can be treated with rules?
A % of them that can be treated with rules? Wow. That is an analysis that I did not perform. So no, but also it depends. You mean the requirements that can be treated with rules, or the specific enrichment tasks that can be treated with rules? There are two different things.
I'm not sure.
But in any case, there is an analysis I did not perform. No.
Right. And I think it's fair to say also that it would be a separate answer for the case of semantic enrichment and another answer for the case of the rule processing. For the code checking.
Yeah.
But apart from which, I think one of the limitations would be that the big set of rules that you selected were not selected to be representative of the overall content of those codes, but rather to be exhaustive in terms of the kinds of concepts that they expressed.
Yeah, I agree.
So unfortunately, it's very hard to say. All right, we are already at 4:30 and time has gone by very quickly. And it's been a really interesting discussion. And I know that many of the participants, Tanya, are really interested both from overseas and from here, because there will be a lot of follow-on to this work. And I think you've really set the foundation for people to go on and explore further in new ways and additional ways to apply it to semantic enrichment. So thank you very much for that. And for those who are here, we will just add that if you have a recommendation for a postdoc, then this is the commercial request part of the lecture. Thank you, Tanya. Thank you, everybody else. Once again, let's raise a hand to Tanya and thank her for the lecture. Bye-bye all. Please feel free to turn to Tanya if you do have any more questions or if you need any material from it. Bye-bye.
Bye.